Okay. So I had posted 2 videos regarding iron carbon diagram. I see that a few of you have seen that. It is essential that you go through those 2 videos which are explaining to us the basics of the iron carbon system. Okay. Anyone who has seen that? Okay, no problems. So we now start our discussion on the iron carbon system only, but we move ahead from the basic phase diagrams, and today we talk about a concept of TTT diagrams, which we say is called as the time, temperature, and transformation diagram. The term transformation here refers to phase transformation. So we are talking about the phase transformation. So if you remember this part of the iron carbon diagram, we have seen that when you talk about this particular composition, which we say is in the hypoeutectoid region, we have said that when you start cooling it, the transformation happens when it hits the alpha plus gamma line. So in this region, you have a phase which we say is alpha plus gamma. So you have a lot of gamma phase in which there are precipitates of alpha. So alpha starts precipitating. Obviously, this precipitation will take time. It is not an instantaneous process. We have already said that it is a time temperature transformation concept that we'll be referring to, and this what we refer to as transformation is also called as phase transformation. So your alpha gamma phase is transforming in this region into 2 phases, that is alpha plus gamma, and when it comes back here, again a transformation is happening where you get alpha plus the cementite phase, alpha plus Fe3C, and that's what we see is happening here. So these phase transformations are time dependent also and temperature dependent also, and we will try to understand today the concept of time, temperature, and transformation. Are you able to hear me clearly?
Yes.
Okay. So we will try to understand this clearly here, that what is the concept of this TTT diagram and what is this phase transformation phenomena means to us. One thing is clear, that a change of phase is what we are saying is termed as phase transformation. So a single phase may be going into 2 phases, like gamma goes into alpha plus gamma, or those 2 phases further go into another 2 phases, that is alpha plus cementite. And let us see how we move forward in this understanding. So this tells me simply that in a phase transformation, what is happening? At least one new phase is formed. At least one new phase is formed. So if you remember the previous slide, you said that here it is only gamma, here it is alpha plus gamma. So gamma is still there, but a new phase alpha is formed. Here it is alpha plus Fe3C. So alpha is still there, but a new phase cementite is formed. So that is the meaning here, that at least one new phase is formed which has different characteristics than the parent phase. And what is of importance is that this phase transformation does not occur instantaneously. This does not happen instantaneously. They begin by formation of numerous small particles in the new phase which grow. So when we talk about formation of new particles, you are talking about first term. In simple words, I will say it is called nucleation. When we say in this gamma phase, let us say I have this gamma phase here. in which on this boundaries you have nucleation of the second phase, nucleation of the alpha phase, and then is the growth of these. So then these alpha crystals start growing. So the two parts of any phase transformation are nucleation of the new phase and growth of the new phase. So it nucleates. So in a scenario here, you can say here that okay, it may nucleate at many of the points here. It may nucleate at many of the points, and then it will start growing at these points. This is nucleation and growth, the difference. Okay. So when you try to define nucleation, we say it involves the appearance of very small particles or nuclei of the new phase which are capable of growing. And what happens during the growth stage, these nuclei then start growing and the grain size then increases. The concept of nucleation and growth will be used in understanding one concept of the grain size today. In very simple terms, I'll try to explain it to you. Okay, so the same thing happens, similar thing happens once you are talking about solidification from a molten metal. So we have said that okay, alpha gamma, which is already a solid phase transforming into alpha plus gamma, but it is also possible that a molten metal can solidify and then it will also involve nucleation and growth, these two phases. Okay, so here just try to understand the basic mathematics I'm ignoring behind these curves here. So what we are trying to plot here is temperature versus rate of transformation. We have said that a new phase that is growing, that is developing, will have two parts to its growth and development. One of them, and the second one is growth. It will nucleate and then it will grow. Now, the rate at which the nucleation happens is shown here with the help of this green curve. Nucleation rate. The rate at which the nucleation is happening is shown with this green curve. The rate of growth is shown here with the help of this blue curve. And the red curve then shows the net transformation rate. The net transformation rate, which is a combination of both. The net transformation rate is a combination of your growth rate and nucleation rate. And we see that I'm talking about the molten metal here. So the upper extreme, this temperature here is T melting point. This is melting point here. We will use the same concept in our other understanding also about the phase transformation when it is a solid to solid transformation. But right now we are saying that it is happening because of your what we refer to as liquid to solid transformation. So we are saying that the three curves which are available to us are, we have one of them is called the growth curve, the rate at which the growth will happen, the rate at which the nucleation will happen, and the rate at which the transformation, the net transformation will be happening. And what we observe is that the maximum transformation rate is achieved not near the melting point, not very less than the melting point, but somewhere midway, when this delta T, the delta T is the driving force for this, what we say, change of phase from liquid to solid. It is happening here. And please keep it in mind one particular issue, that the growth rate is maximum at high temperature and at It is very important concept which makes us understand the further concept about the size of grains or grain size development. So we are saying here that the growth rate here is happening is maximum near to the melting point or near to the transformation temperature. This melting point is replaced by what we call as the eutectoid temperature in the case of our steels, and that is where we will use this concept that when you start cooling steel below the eutectoid temperature, the when the delta T is less, the growth rate is maximum. When you have more delta T, when you keep on lowering the temperature, nucleation rate will be maximum at lower values, and the net transformation rate will be governed by this red curve here, which achieves a maximum value at somewhere midway. So this is the basic concept. Okay. As we said, that the transformation from single phase, let us say from your gamma to gamma plus alpha, this does not happen instantaneously. It takes time. So we are saying now we define one term called as transformed fraction with respect to time. So we are now talking about the time concept. Earlier we said that was equilibrium diagram, and we say okay, it will take very large amount of time, very slow cooling, but in actual scenario that does not happen, and that is why timing is important. We shall understand and measure the time also. And what we have been able to plot is here the fraction of the transformation, that how much of the fraction of the phase transformation has completed. You start from 0, means transformation started from here, and here the transformation is complete. So you started with only gamma. Here I have gamma plus alpha, whatever has happened, complete transformation is here at 1. And it takes this particular red bell-shaped curve or S-shaped curve, which we say is the transformed fraction versus time curve. So we find here that this is log t, logarithmic log of t. So it is observed here that on a time scale, when you start from 0 time, at passing certain amount of time, here the nucleation portion is happening. So the curve is almost flat, it is not visible that way. Then we find that it starts doing this way, and then here we have our completion. So your what we call as the phase transformation is complete, and we call this as what we refer to as the transformed fraction versus time curve. Okay, so after going through this particular curve here, we will try to now combine it with the help of one more diagram. So we have one concept of transformation now, phase transformation versus time, that how much time it is taking to cause this phase transformation. And we will try to go forward with this concept here. Okay, so we see here that it is possible for us to plot these S-shaped curves at different temperatures. So you can see these curves can be plotted for different temperatures. And we see that this is how it has been done for maybe copper at different temperatures, 135, 119, 113. That way, you can say that you can be able to plot these transformation curves at different temperatures. And if I am able to plot each of these curves at a different temperature, which is constant, we say this is a curve for isothermal transformation. Isothermal transformation. Okay. I come back to this curve here. We say is the rate of transformation curve is here. The rate of transformation is maximum at somewhere here. And when I plot it in place of plotting rate, if I plot the time, we find that you get a inverted curve. What is the fun of inverted curve? It is just coming up. Let us see what is a TTT diagram now, which I said that we'll be discussing about time, temperature, and transformation diagram. So you have the rate of transformation curve, which I've already explained. Then you have this, where we say is the fraction transformed curve. So you can plot this fraction transformed at different temperatures. And here we now plot temperature versus time, log T. So you are plotting temperature versus log T. What we do that at different isotherms, at different temperatures, let us say I'm talking about this particular temperature T1. At this temperature T1, I plot the fraction transformed curve. As I said, that you can plot it for different different temperatures like this. So you plot it for one temperature T1 and mark the starting of transformation here. The starting is happening, and we say that here the finish is happening. So I do it like this: start of transformation, and this is the end of transformation. Similarly, at a different temperature now, we plot another similar S-shaped curve. When I do that, it may give me that okay, this is the point of start of transformation, and this is the end of transformation. We keep on doing that, and then I plot again start of transformation, end of transformation. Then I see again start of transformation and end of transformation. And then once I have done that, we can then join these lines here. The start points are all joined, and then we join the end points now. So I get two C-shaped curves. One here is about the start of transformation, and here is the finish of transformation. Starting of transformation and finishing of transformation. So it is plotted like this now. And keep it in mind what is here of temperature. We already said that near to the melting point or near to the eutectoid temperature similar to the melting point, we have small driving force for nucleation, means growth is more prominent. And here at the lower values, nucleation is more prominent and growth is slow, growth is sluggish. What happens because of this? Let us look at this now with the help of another one. So when I say it is about a liquid to solid transformation, we are saying, let me go to the next one, we will not use, okay. We talk about this liquid to solid transformation, we are saying that if this is the melting point, the dotted line, melting point, these two curves we have seen, which we have plotted, we have been able to plot with the help of your previous example. So this is the start curve, start of transformation. This is the end of transformation curve. And the transformation percentage is increasing. Here it was 0, here it was 50, here it was 100. Total transformation has taken place. So let's say 99% finish, 1% to start. And what I achieve here is liquid which is unstable, which wants to transform into solid phase. So this transformation can happen at various temperatures. You can say that okay, when you take liquid here which is above its melting point and it follows this black curve. The black curve is the cooling curve. So you reduce the temperature, you cool it. So the cooling curve follows this black line. Obviously it is taking a lot of time and the slope of the cooling curve is less as compared to the second curve, which is taking less time as compared to the first curve, and its rate of cooling or the slope is higher. I can say it is fast cooling because it is taking less time to reach from the melting point to the same temperature, to the temperature here. So it's the temperature line here, temperature axis. Or I can have very fast cooling where it takes very less amount of time. The time taken is very less here to find for the cooling to start to complete. So it is taking very fast cooling route. It can take very, let's say, fast cooling route, or it can take the slow cooling route. The question is, what will be the difference in the grain size when you go for slow cooling or fast cooling or very fast cooling? The difference is that we already said that at our temperatures near to the melting point, the growth rate is dominant and there is less nucleation. And at lower temperatures, nucleation is dominant and the growth rate is less. What is the result of that? It is here that when you are cooling it through slow cooling, you are melting and then cooling slowly to achieve a solid phase from a liquid phase. What you achieve is that the growth rate is more dominant, the nucleation sites are less, but they grow very fast. So they will have large grain size or coarse grain size. Large grain size or coarse grain size. So coarse grain size is here. And then what happens at lower temperatures, we have nucleation which is dominant, means many nucleus will be formed. Large number of nucleus will be formed. There will be tendency to have large number of grains, but they will not grow much because the growth rate is sluggish. And that is why the size that you obtain here is smaller or fine grain size. Does anyone remember that what was the effect of achieving a fine grain size on the strength of the material? Do you remember that? The Hall patch effect? Yes. Anyone, please? Can you hear me? Is my voice audible to you or no?
Yes, sir, your voice is audible.
Okay. So if you remember the Hall patch effect, we had said that a fine grain size is better for us. That a fine grain size will give you higher strength material, and that is where we say grain size refinement or grain size strengthening, or strengthening based upon the grain size reduction was there. So you are able to see here that by slow cooling we achieve large grain size, and by fast cooling we achieve small grain size. So we may be able to achieve slow cooling or fast cooling, and then maybe strength can also be developed based upon this. So this is the basic concept of the time, temperature and transformation diagram. For LS transformation means liquid to solid transformation is what I am referring to right now. With the help of this diagram, now we shall be able to further progress into the phase system diagram of your iron carbon or iron carbide system, and the concept of TTT diagram we will try to apply to the eutectoid steels. And let's come to this phase diagram. So we understand here that this is the region which is more important to us for steels. This is the hypoeutectoid region, and here is the hypereutectoid region. We have the hypo and the hypereutectoid region. We now will see that how does you plot the TTT diagram, time temperature transformation diagram, for your hypoeutectoid steels or eutectoid composition or any such composition, and why do you call it a TTT diagram? Okay, so let us come back to this topic. What you see up here, the top view, this figure is nothing but the fraction transformed diagram, which you have plotted at, let us say, some temperature. Let's say I say it is at 675. So we plotted it, and then this is 720 degrees, your temperature above which austenite is stable. Just see there, it is 723 degree or 720 degree, and you are above that, that is you are in the austenized state. or austenite phase is available to us here. You are here above that. So when you lower the temperature to 675, which is below the eutectoid temperature, it is expected, what is expected, that gamma phase, single gamma phase, will transform into alpha plus Fe3C, which we say for this composition is called perlite for your particular composition. So we see here that this is gamma plus Fe3C reaction which will take place, and how much time it will take that we can see with the help of this fraction transformed diagram. The transformation we say is beginning here and is ending here, and this is the fraction transformed. You start with 0, 50, 100, and then I plot it on this diagram as I said in my previous slides. So you have the starting curve, starting point on the curve, and the final point on the curve. Similarly, you are able to create this begin curve, red curve, by plotting many such transformation fraction transformed diagrams for different temperatures. So you do it for 675, then you do it for 600, so you may reach here. So this may be your 600 one. Then you go for 500 something, so you may reach here, start and beginning. And when you join these, you create this curves, these two seed shape curves. And this curve is actually combined one is called as the TTT diagram. What is, because this curve, the lower one, the lower diagram is telling us it is a diagram between temperature time and time. So you have time and temperature, and these two curves are the transformation curves, the start of transformation and the end of transformation, and that is why the third T comes into picture. So it is time, temperature, transformation diagram, and this is how it goes, like time, temperature, transformation diagram. And you have in between the blue dotted line which says it's a curve which tells us about the 50% completion. How we will use it, we will just see. This diagram actually gives me an idea that you may be able to control the grain size development if you are able to cool it somewhere here in this region. You said that high cooling rate, slow cooling will give you coarse grain. Slow cooling may give you fine grains here if you cool this way. But what you are assuming here is that this transformation right now is happening at this constant temperature, at this isotherm. So we are saying that this transformation, TTT diagrams, are also known as isothermal transformation diagrams. We are assuming that this transformation is happening at constant temperature. That is because this is what you are plotting here, that the starting and ending. Similarly, starting and the start point and end point, they are happening at the constant temperature, and we call it as isothermal transformation curves also. So when you look at this basic diagram now, where we see now the temperature axis T, the eutectoid temperature above which you have gamma, which is stable. Here it is also written austenite, but it shall be written as unstable. It is unstable. It is ready to be transformed. Above gamma, above eutectoid, it is stable. And what we achieve is that when you cool it at different cooling rates, you achieve perlite, you achieve perlite plus bayanite, or you may achieve bayanite only, or you may be able to achieve martensite also. And we will see that what is the difference between these two, these various terms here. Just a minute. Okay. So if you look at one of the temperatures here, we are saying that plotting the same TTT diagram now. Temperature versus log T time, and the start of transformation and the end of transformation curve. The eutectoid temperature. So above that, austenite is stable. In this region, you have austenite again shown, but it is unstable, ready to be transformed. So what you do, if you undercool this solid from 727 to, let us say, 625 degrees, and then hold it at this temperature. If you isothermal hold, if you hold it at this temperature and allow the transformation to happen from C to D. So this is showing you start transformation now. So what is observed is that this gamma will then transform into perlite, that is alpha plus Fe3C. And it will take this much amount of time at a temperature 625 maybe. And at the end of it, here you may get what we get as perlite, which we say is written as coarse perlite. We have said coarse perlite because it may be possible for us to cool it further down. You may cool it up to here and then hold it isothermally. So then it will pass through this curve. It will take some time for transformation to be complete. And I may still get perlite. It may be fine perlite now because you are having a cooling rate which is faster than your the first case. It is coarse because here the growth is dominating. That is why the grain size happens to be coarser. Okay, so when you talk about the TTT diagram for your iron carbon system, this is what is observed. So when you take eutectoid temperature, when you start cooling it and then you start actually isothermally holding and transformation happens at a temperature T1, at a higher temperature near to the eutectoid temperature, you may get perlite. If you are in the above region, you may get coarse perlites. Below region, you may get fine perlite. If you cool it moderately here and then follow this curve and then transformation is happening at this temperature, you get perlite plus another compound which we say is bayanite. It's not again perlite, as we said, is not a phase, it is a constituent. If you go to T3 and then carry out this isothermal transformation, it will give you bayanite. But if you follow very fast cooling rate, this one, if you follow this curve and you avoid, we say this region is called the nose of the C curve, because here we are saying that transformation is not happening. Transformation will happen once you touch upon this curve and then the C curve passes through this, transformation line passes through this, and then the transformation will happen. If you are able to avoid the touching of the nose of the C curve by cooling it very fast, let's say I cool it very fast, this is what is happening, I cool it very fast, you do not produce perlite, you do not produce bayanite, but you produce a what we call as martensite. Martensite is formed once you do go for very fast cooling, or you cool at a rate which is greater than the critical cooling rate. And the basic concept is that you have to avoid touching the nose of this curve here. If you pass through this curve, the curve is here and the cooling curve is passing through this region, you will start forming martensite. So you avoid the nose of the start of the C curve and cool below the martensite formation or finish temperature. We form what we refer to as martensite. Martensite happens to be the hardest component in steel, and that is the basic fundamental through which the your steels are hardened by quenching them. So this very fast cooling can also be termed as quenching, rapid quenching, means water-based quenching or oil quenching. Anything is possible here. So fast quenching will give you martensite. How fast? You have to avoid the nose of the cooling curve here, which is available for all the steels with you. So we get here now the TTT diagram, and then we say martensite, how it is formed. If you are taking this material here, and if you start cooling it from here, it touches the line, and then isothermal transformation happens, and you form perlite here. When you start cooling it very fast and you do not allow the cooling curve, so this is your cooling curve. When you do not allow it to touch the nose of the C curve here, so this is the starting of the transformation curve. This is the ending of the transformation curve. And when you do cooling at a very fast rate, we achieve what we call as Martensite transformation. You have Martensite formed here. Martensite, as we say, is the hardest form. Okay, I will come to this continuous cooling later, but right now, what we are able to understand is that you have the concept of what we refer to as the TTT diagram, and you are able to explain that by cooling at different rates, we may be able to form different micro constituents. You may be able to form perlite, or you may be able to form martensite. Martensite, for your information, has got body-centered tetragonal crystal structure. It's a metastable phase, and then one of the another basic advantage of forming martensite, basic difference in martensite formation is that this martensite formation is a diffusion-less process. Why? Because you do not have time for diffusion. You cool it at such a fast rate that there is no time for the atoms to diffuse from BCC, from FCC into BCC or different phase that way. It is a diffusion-less process. Whereas the other transformations, the perlite or bayanite or they can say the normal perlite formation, it is based upon diffusion. We have explained it already that why diffusion was necessary, because the composition of gamma and alpha and Fe3C are different, and to have that you need to have diffusion going on, whereas martensite formation is diffusionless. Any questions here, please? Any questions? No questions? Anyway, so this is, as far as what we said, is the understanding of the TTT diagram is concerned. That what is the time versus temperature versus transformation diagram. So this explains the concept of the TTT diagram. I hope it is clear to you. Okay.